Good day. Welcome to today's lesson. This is lecture 1 and we will be looking at an introduction to the discipline of building science and construction. So let's start by first defining what building science is. So building science is a field of knowledge that draws upon essentially your hard sciences such as physics, chemistry, engineering, architecture, and your life sciences such as biology, anatomy, things of that nature. It is also the understanding of the physical behavior of your building as a system. So remember, a system is something that is made up of different parts that work together for a common purpose. It also involves the understanding of how that system impacts energy efficiency, durability and the strength of the building, the comfort of the occupants, as well as your indoor air quality. And all of these things contribute to the what we would call the high performance of your building. So your building actually has a performance. Building science is also looks at the importance of how contemporary building science how it is fully appreciated after the occurrence of building performance problems. All right, so the point we're making here is um, building science is really only appreciated after you have performance problems, when you have maybe structural issues, air quality problems, all of these things arise. Only then do we tend to start thinking about how the building was planned and the design of the building. All right, and ideally this is not what you want to do. You want to actually apply building science concepts and principles in the early stages of your building cycle. So as we're talking about building cycle, let's look at what the full life cycle of a building should look like. Now, it's not necessarily always like this, but this is the ideal. So to begin with, there must be a policy in place that informs the design of your building. What kinds of building codes and building standards are in place. These should You should have national building codes and standards that should inform how your building is designed and built. Once you have that, the next stage you look at would be the planning of your building. So you make a determination. What is the purpose of your building? How do I plan to achieve the purpose of my building? What steps do I need to take? What things do I need to put in place? What resources must I have? Then you must also properly design your building. So that's the next stage. So your design, this is where you start doing your building plans, and this is where the architect may come in, etc. Next stage, you construct your building based on your planning and design that went before. Commissioning of the building, at this stage, this is really essentially where you reach that place where you make a determination that the building has met the conditions and is suitable for the use and purpose for which it was built. You must also have facilities management in place. This is important for building maintenance. So maintenance is not really it's just essentially services and resources that will help keep the building functioning as it was designed to. You must also be prepared for forensics and rehabilitation. So if problems arise, how can I fix it? All right, what resources must you have in place? Restoration and retrofitting, this has to do with if you have degradation, how can I restore and bring it back up to the normal status? Retrofitting would often involve if upgrading needs to take place, and from time to time things will change, materials will change, technologies will change, and even policies and standards would change. So you have to be prepared for retrofitting and upgrade. Preservation and conservation, this is particularly important for older buildings, particularly those that might be considered a national heritage, etc. All right, do you have things in place for that? So those would be like for public buildings. And then of course many buildings reach to the stage where it is considered the late stage, where it's not possible for you to upgrade or restore or retrofit. It would have to be decommissioned and demolished, and those materials can be used for recycling. So this is essentially what our building life cycle would look like. So we're moving on. Why is building science important? So we're trying to answer that question here. So modern buildings routinely leak rainwater. This is often associated with design problems. We have air leakage as well, related to indoor air. This can affect indoor air quality. So where we have structural or design issues, we can have moisture entering the building. We can have the wrong type of air, with heated air entering an air conditioned environment, etc. And these things can lead to damaging or unhealthy condensation. So that can this unhealthy condensation can lead to a buildup of things like mold in your environment, which can now directly and indirectly affect the occupants of the building. They can also lead to durability problems in terms of the structural integrity and strength of the building, which can shorten the life of the building. Okay, and modern buildings demand higher predictable levels of durability. That same strength I'm talking about, energy consumption and comfort. For example, let's look at a public building. A public building would tend to have firstly a whole lot more people in and out of it. As you have more occupants, there would also be greater energy consumption. Typically modern buildings have a greater use of air conditioning that older buildings in the past did not have. So there's greater energy consumption, and all intended for the comfort and convenience of the occupants. Okay, so as I said, there's a greater demand on it. Also for the strength and durability of the building, we have a greater emphasis on building standards and building codes internationally, and even within sectors now. So there is a greater emphasis on these things. All right, let's look at the building system theory. So remember in a previous slide I made mention of the concept of the building being a system. So a system again is something that is made up of several parts or components that work together for a particular purpose. So what we want to do now in building science is we want to treat the building as a system. All right, and what would some of these components within this system look like? So we have observations. So we organize the building by objects, really. All right, so we observe what different objects we have in the building. So it's a way of thinking about how objects and processes relate. So in a system you will have objects, and then you look at how those objects are related to each other. So those would be your processes. So in the building we have objects and we have processes taking place. So the systems approach is also a way of talking about how the parts of this talking about the parts of the system and the outcome of those systems in terms of achieving your goal. So let us look at this in a little more detail. All right, what types of systems do we have in a building? So we can classify those systems into these general categories here. So we have boundaries and boundary criteria. Alright, so many people believe that a building system ends at the outer surface of the building. So that would be like your outer walls. and in some cases maybe the property boundary. But in reality, the building system extends to the outer reaches of what it impacts and what impacts the building. So for example, the building boundary could go to the basement. So the basement flooding, right? So vertically you could talk about basement now. So basement flooding can occur due to municipal sewage discharge, and is an example of building plumbing system extending to the local municipal infrastructure services. So here we're looking at another extension of the boundaries. So all the utility infrastructure, for example, such as sewage pipelines, electrical pipelines, and you can even look at your Wi-Fi network as well. All of these things will actually extend the boundaries of your building, because your building is connected to all of them in order to receive essential services. All right. Then you have flows and storage. What are these flows and storage? For example, your inhabitants, right? Your inhabitants, they come, they go, they move in different patterns, directions, etc. Then we have energy. For example, your electrical services. Even in terms of flows, we mentioned a few examples in under boundaries that can also be listed here. Water supplies, etc., sewage supplies, and data, Wi-Fi data networks, etc. All of those can be listed here. And again, these are essential services required by your building in order to function. So these would be considered an important system as well. Alright, so your occupant behavior is among the most difficult flows to accurately predict in any energy model, because people don't exactly move in a predefined path. So that's essentially what that is. Alright, whereas with the other flow systems, it's possible for you to predict. Transformations, another system. So buildings age and they are modified by their users, not always in a beneficial way. It is desirable from a life cycle perspective to design buildings that can adapt and adopt new technologies to improve their performance and minimize functional obsolescence. So what are we talking about here? Transformation as a system. Your building must be designed in such a way that it can be modified when necessary. You don't want to have such a hard, rigid design that when it's necessary for you to upgrade and retrofit, that it is impossible for you to do so. That's not good building design at all. Okay, additionally, another system, spatial and temporal hierarchies. So passive survivability and safe, secure building design are premised on achieving spatial and temporal resilience. So spatial as in like geography and location, and temporal as in what is happening at that particular time. Is your building resilient in those particular contexts? For example, with regards to spatial, is my building location resilient to the natural landscape? Is the location affected by natural and man-made disasters? Does it have a propensity for those types of activities? Is it resilient to hurricanes, earthquakes, etc.? Temporal resilience, for example, in Trinidad we have seasonal changes from one season to the next. Rainy season, dry season. Is my building resilient to floods? And anything that can change, as a matter of fact, with time. It doesn't have to be weather only. It can be, maybe it could be civil unrest. Is your building resilient to vandalism? Things of that nature. Alright. And then there's the feedback and control loops. So here it's important for us to know that buildings are prosthetic extensions of the human body. So prosthetic as in, like, for example, um, an artificial limb extension, right? And as such rely on many forms of cybernetics to control your indoor environment and maintain safety and security. So in terms of your environment, your building would often require technology to control that, as well as with regards to safety and security. Technology is often employed to meet these requirements of your building. So these are also systems of the building. All right. So this little schematic here is just a visual representation of some of these systems we were talking about. So here, for example, we have our outer boundary of our building. So that's one. We have our inhabitants, as we mentioned in the slide before. If you look up here, you see this label highlights our mechanical and electrical systems. So at the top, this is where we would have a lot of our controls that manage indoor air quality, electrical power, and things of that nature. Down here, this would be our basement section of our building. This is where we would have sewage networks, plumbing, etc. And then this is our external environment, which would also affect the functioning and performance of our building. All right, so this simple little diagram you would need to know and be able to explain in the context of what we have discussed already. All right, so physical forces and how they affect buildings. So some of the physical forces that we would need to take note of, for example, would be heat flow. So we know, if you think back to your basic general science and maybe even physics, we know that heat can flow via conduction, convection, or radiation. We would look at that in a subsequent slide, just to make sure that we are able to make some kind of real life connection with it. Then in addition to heat flow, we have airflow. So the air flows across and within building enclosures due to air leakage and ventilation. So within the building context, we need to be concerned about those gaps in the building structure and building design that can lead to the leakage of air out of the building or even into the building, and also what your ventilation, how your ventilation has been designed, and how effective it is, because airflow would also be determined by your ventilation. Then there is also moisture flow that we would need to be concerned about, the flow of water and vapor across and within your building enclosure. So for example, through walls and windows, etc., you have to be concerned not only about heat and air, but how are you able to control the moisture coming in and out of your building. And additionally, solar radiation. So the influence of insulation on opaque and transparent enclosure components. So we're talking about things like your walls, if you have glass windows and walls on the external part of your windows, your external part of your doors, sorry, or walls, because this can influence the efficiency of your energy use in terms of air conditioning, and also the level of comfort of the occupants in the building. Right? So that moves us into our HVAC system. So when we talk about HVAC, we're talking about heating, ventilation, and air conditioning systems. Now during cold periods, heat and warm moist air escape through leaks in the building enclosure. Alright? So this would be typical of what happens in temperate countries during winter, for example. heat from inside the building, heat and moisture from inside the building can escape. To compensate now, the heating system will have to work overtime in order to provide the heat that has been lost and to replace the moisture, so that the building will be more comfortable for the occupant health and comfort. During hot periods, this is more typical of what we might experience. Heat and moist air are driven into the building, okay, from outside. What happens then? Heating, ventilation, and the air conditioning, again in this case, must work overtime to provide the opposite of what happened in the previous point there. So it has to work overtime to cool the environment and also to dehumidify the environment to make it less moist. Because where you have the presence of moisture, especially built up over time in that enclosed environment, it can become a health hazard. Okay, so here we conclude this section of the lesson. We have a part 2 to continue on to. This section of the lesson, we conclude with a very important statement. Alright, the key to the fitness of a building is the balanced control of these physical mechanisms so that the durability, that is the strength of the building, the comfort of the occupants, the energy efficiency used within the building, indoor air quality, health and safety are not compromised. So this is a very important statement. Within that statement, you see all the essential components of a healthy building contained within that statement. So please make sure that you clearly understand this statement, and that if you are asked to explain or describe a healthy building, that from this statement you can actually identify all the characteristics of a healthy building. Okay, so at this point I would just like to ask you to please proceed to the next part of the lecture, part 2.